Okay, we are live. So everyone, thank you very much. We have Marianne Bellotti with us. Marianne has been a guest on the Legacy Kid Rocks podcast. I had a wonderful time chatting with her. She also has a book that she came out with recently called Kill It With Fire. It's very entertaining. And I'm looking forward to hearing what she has to share with us today. I'll let you take it away, Marianne. Thanks.
Hi, everybody. It's such great honor to be here. I'm so looking forward to talking with you guys about really two of my most favorite topics in one talk. Today, I'm going to talk about modernizing legacy systems using what are called formal methods, or sometimes you'll hear me say formal specification or formal verification. There is a difference between these three terms, but for the purpose of this talk, I'm just kind of use them a little bit interchangeably. So essentially, how do we model computer systems in order to improve maintenance, improve modernization efforts, and ultimately restore things to operational excellence? You can find me on most channels under the handle Belmar, on Twitter, on Medium, on most social networks. That's where you'll find me. And as has already been mentioned, this year I had an amazing accomplishment. I published my first technical book. It's called Kill It With Fire. It's all about the things that I learned running large legacy modernization projects for the United States federal government and for a lot of really complicated bureaucracies. I tell people that I have 15 years as a software engineer. That's not quite an accurate statement because I started writing code when I was 14 years old, but I'm not really sure how much of my script kiddie passed to count as professional experience. So I just sort of peg it as 15 years as a nice number that I feel solidly no one will complain about. There was a period in my very early career where I very much did not want to be in computers because I saw that as primarily super boring and merely about math and science. And I was interested in people and organizations and structures and economics and things like that. And so I went and I did most of my formal education in anthropology. And that really heavily influences what I do with technology today. Because what brought me back into technology was realizing that technology doesn't exist in a vacuum, that it's a combination of organizational incentives and technical realities that create a lot of these complex systems and determine their life cycle. And so for a very long period of my career, I was focused on legacy technology. And lately I've been looking at the lessons learned in that space, and with that experience, how do we apply that to cutting edge technology today? Because they're broadly relevant to all complex systems. And that was my motivation around writing the book, but it was also the motivation that backs a lot of the stuff I'm going to talk to you about today, which is a real area that I'm passionate at. So let's start off with, what do I mean when I say modeling systems, right? And so the first thing that I think is really clear to understand is that when we talk about modeling in this space, we're not talking about visualizations. We're not talking about diagrams. We're talking about abstract representations of the interactions that make up a system, in this case, a computer system, and that these are runnable representations. So they're not diagrams, they're code, they're bits of code that can be executed to basically model different scenarios. And ideally, when we say we're runnable, we also want them to be checkable, which means we can make a list of assumptions or statements, and generally we call these things constraints, and we can program them into the model and have the model check itself to see if those constraints, if those rules are valid. And we're going to go into those concepts in much more detail. But that's what I want you to think about is when we're talking about modeling here, we're not talking about just documenting what a system looks like visually. We're talking about documenting it in a way, specifying it in such a way that we can use other computer programs and other tools to kind of help us with some more critical thinking about these systems. Well, why model computer systems? Typically, a lot of the modeling world focuses on stuff that's in development. We're in that kind of early research phase. And the argument that's made for modeling systems is that there are a lot of bugs that happen only at certain scales and are really subtle. But as soon as you get hit with them, they're super obvious. And so hindsight is always 2020. But by modeling systems, we allow us to take a peek into the future and get some of that hindsight perspective before we built the system. Because you don't know what you don't know, right? And this is broadly true in any field, but it's especially true when you're dealing with complex systems and computers. So when we model systems, we get to explore different scenarios. We get to answer some really critical questions about complex systems in general, meaning we have a certain set of expected behaviors, but do any of those expected behaviors lead to unexpected ones? And it's so, under what conditions do they lead to those unexpected behaviors? Like, if there are things that we think are impossible for this system to achieve, and there actually are possible, why? What causes a system to reach an impossible state? And so models kind of help us reason about systems and deduce some of those known unknowns and kind of like narrow the field of like possible things that are going to catch us by surprise. On legacy systems, we have some additional advantages in that the real critical component of modernizing a legacy system is always about prioritization. Like I generally find that the things that people struggle with when they're trying to modernize systems aren't really the technical challenges. The technical challenges are pretty straightforward. Sometimes they're complicated, but they're in terms of like what is broken and what has to be done in order to fix it. It's usually not a huge like brain teaser type problem to figure that out. It's just figuring out in what order do you do it and what urgency level do we do it at? If we're also rolling out new features, like where do we do it in the like normal rolling out of new features? Like it's all that prioritization. That's the really hard part about dealing with legacy systems, right? And we not only need to figure out that prioritization, we also need to be able to effectively communicate that prioritization to other people of different technical levels. And so as we're making changes with systems, being able to predict where potential problems might be triggered by improvements, to get in front of those problems, communicate why certain changes are more valuable at certain times than other changes. These are all advantages that models can bring to the table. So where does software typically go wrong? And I'm sure that people in this conference have lots and lots of experience and lots of opinions about where software tends to go wrong. But the three areas of unknowns that I want to talk about in detail in this talk are algorithmic correctness, concurrency, and relational issues. And I'm going to go an overview of each of these core areas, and then we're going to do some use cases in each area with specific technology after that. So let's start with algorithmic correctness. For most people, when they're talking about like, does this algorithm do what it's supposed to do, they never really move beyond the unit testing or the fuzzing. Like if they get to the fuzzing testing, like that's like the advanced stuff, right? So like most programmers assess whether an algorithm is doing what they think it's supposed to do by taking a set of inputs and a set of known outputs and then writing a bunch of tests where we demonstrate that given an input, a function returns the desired output. And then they might go a step further and say like, well, let's give some variables that we don't know the outputs to, the fuzzing aspect. Let's give some different types of inputs that we feel like shouldn't work or shouldn't produce a correct response and put it in there and see what the system does, right? But those types of testing, although they are super useful and super valuable, they don't really establish that an algorithm is correct, right? Because no matter how many tests you write, you haven't covered all of the potential edge cases with that test, right? So when we're talking about algorithm correctness, we're really talking about writing a proof of a given function to assert its mathematical correctness over its just anecdotal ability to take an input and produce the correct output. So we're really talking about, is this correct for all possible inputs? And are there any undefined states that is not covered by any other form of testing? So one of the potential tools we can use to do this is Z3, which is an SMT solver. SMT solvers and their cousin AST solvers are basically programs that solve logic puzzles. And so the code that you write for an SMT solver is this series of true-false statements that make up a puzzle. If you've ever had any exposure to a language like Prolog, you're already somewhat familiar with what SMT looks like in the wild. It's the same sort of idea of like we are establishing these true-false statements and then running a program that will make deductions based upon the inputs and the rules that we've given it. So an example of a logic puzzle is something as simple as all men are mortal, Socrates is a man, is Socrates mortal? Everybody should know how to deduce the answer to that question really easily. And that's the types of relationships we're talking about. We have this implies this statement is true. Because we know this statement is true, we also know that this statement is true. But we can take that core concept, that very simple concept of taking true-false statements and the relationships between them and making deductions, and we can build it out to more complicated puzzles. Generally speaking, when people first start getting exposure to logic programming, the first thing that they are asked to do is write a Sudoku solver, because that seems like a really hard challenge, but it actually can be like represented in logic in a pretty straightforward manner. Every square in a Sudoku puzzle has a certain set of states that are valid, right? So you have that square can have the value of 1, it can have the value of 2, all the way up through 9, right? And so each one of those possible states is essentially a true-false question. Is this square, does it have the value of 3? Does it have the value of 4? So on and so forth. And when we have inputs, we have a different set of rules about whether numbers can be in the same row, whether numbers can be in the same square. And so given those different logic rules, the relationships between what states can be on at the same time, we can essentially write a lot of true-false statements that create a puzzle that the computer can then take a set of known states and deduce what all of the other states are. And so we can do this with Sudoku. We can do this with what's called the zebra problem, which you've probably encountered as a word problem that goes something like this. There are 5 houses. The second from the left is yellow, and the person in there drinks milk. The third from the right is blue. The one next to the greenhouse is the red house. And which house has the zebra, right? So that's another style of logic puzzle in which we're given a certain amount of states that we can represent as true, false. We're given a certain number of inputs of known states that are true, and we deduce the rest of the states. The same with the 8 queens problem, which is another one that's very popular with logic programming. But all of that is really fun and interesting and compelling, but sometimes difficult for people to map to actual things that programmers do. But when you really start to get into it, you realize that things like optimizers and schedulers and verifiers can all look like logic problems. We can establish a certain set of states and represent them as true-false questions. We can build relationships between those two true-false scenarios, what can be true at the same time, what must be false if the other state is true, and then we can then deduce a different set of states and valid conditions based upon those inputs that we give something like S3. And so a really easy way of thinking about like how this applies to programming is types. If you're familiar with how type systems work at all, they are represented as a series of logic rules. Like we define a type based on what it can and cannot do with other types, and operations based on what they can take as inputs and what they can take as outputs. So this is an example of a programming concept that we use every day that is fundamentally just a set of logic rules, right? So that brings us to the second category, concurrency, otherwise known as time. We live in a world of distributed computing. Like we have multi-cores, we have cloud. Like when an algorithm is doing its work, it is more and more common for the steps of the algorithm to be spread out across a distributed network of processes or services, right? And so that opens up the question of, well, the steps of this algorithm, if they're done in a different order, does that matter? And often the answer to that question is yes, that there are certain parts of the algorithm where you need to do the steps in a particular order, and there may be certain parts where it can be more async, and that's fine. And generally what we do is we know which steps need to be done in a specific order, and so we build some controls in to ensure that those steps can't be done out of order. But we need to assess that those steps actually work, right? So the first thing we want to model is like what happens if these steps of this algorithm are done out of order. And the second thing that we might want to model is the controls that we've written to prevent those steps from being done out of order. Are we sure that they work under all conditions? And so a great tool that we use for doing this in the modeling world is called TLA+. And essentially what you do in TLA+ is you define your algorithms in a series of steps, and then you set some constraints as logic rules. What's great about temporal modeling, which is what TLA+ does, is that you have the option of doing straightforward true-false statements, like with normal logic programming, but you also, because you're factoring in time, you can also do logic statements like this thing will always be true throughout the entire lifetime of the model versus this thing at some point when the model is running, this thing is true. But at other points, it may be false, and that's a valid state. And so once we've set these logic constraints, when we're running the model, we're looking for, is there an order of steps that violates those logical constraints? Okay, last one, relational. And by this, I mean permissions primarily. So because we live in a world of complex systems, we're also generally dealing with fine-grained permissions. We might have user groups, we might have user roles, we might have hierarchy between those groups or roles where we're inheriting permissions from another group that we also belong in. We don't always have the luxury of having really simple data schemas in our relational databases, right? We may have circumstances where even something as simple as like a user uploading a profile photo, like are they allowed to have multiple photos, right? Or do they just have one? And what are the relationships between those data points in our system look like, right? And then on the more basic level, we have system-to-system interaction. Like how do these systems relate to one another? And like what are the permissions between them? So all of these are things that can be represented in relationships really easily and reasoned about in relationships. And so for that, we might use a tool like Alloy, which is basically structured around hierarchical relationships and asks us to define different types of things. In Alloy, they're called signatures, and then specify the relationship between these different types of things. Like how do they relate to one another? Is it a process that's shared between them? Is it a parent-child relationship? And then we, again, use logic to make assertions about what relationships are valid. And then Alloy is actually built on top of an SMT solver. And so it translates all of that into SMT and solves the logic puzzle for us. Okay, so at this point, all of this probably seems extremely abstract and kind of difficult to grok. So I want to get you into something a little bit more pragmatic, some use cases around actually doing this with technology, right? So about a year ago, I had this one particular project where the engineering teams were working from a shared set of requirements as normal, and like everybody had different interpretation of what the requirements were. And the way we solved this was by using modeling. So we need to add some new functionality, but how do we get everybody to agree on what the functionality actually is? So there are some basic things that we can do, right? Like doing wireframes or mock-ups of the new functionality and like what the experience looks like. That helps a lot, helping people visualize like what we're describing requirements. We can write very detailed requirement documents that kind of specify all of the various scenarios we can think of. That helps too. But just as unit tests don't cover every conceivable form of input and output that we could come up with, detailed write-ups don't cover every conceivable scenario either. And it's somewhat advantageous to write computer programs that are capable of covering every possible scenario. And so what we do with Alloy, again, we define the types of things, we define the relationships between them, and we make assertions about valid relationships. And what's really helpful about Alloy is that Alloy doesn't understand the abstractions that you're presenting it with. So it'll just give you every conceivable valid relationship, even ones that are nonsensical to you, and it stimulates really great conversation. So when we're talking about relationships here, we're talking about hierarchies, we're talking about the taxonomies, things like that. If you can make your situation, your requirements look like a hierarchy or a taxonomy, then you can model it pretty easily in Alloy. So in the situation that I was in, what we were trying to build was essentially a forensic pipeline, right? We had a set of devices with a whole bunch of files. And we wanted to make it easier for people to kind of go through the files on these devices and find significant things in them. So what they wanted to do is they wanted to kind of run analysis over the files on these devices. And when there were pictures that seemed to have people in them, they wanted to cluster the pictures of similar people together. So these will all seem to be the same person. And they wanted, when they were documents that had proper names in them, they wanted to cluster the documents that mentioned the same proper names together so that forensics analysts, when they were going through these devices, could kind of do it more quickly. They could kind of go to the areas where it seemed to be that there was something of interest there. And so what did the model look like in this case? So the types that I was defining when I was building out this model were the device. And then I'm like, okay, on the devices, we have faces and we have names. Actually, when the first draft of this model, I was like, okay, on the device, there are files. And then on the files, there are faces and names. And then as I was working with it, I was like, actually, we don't really need the file part. Like the file part is there, but we don't need to specify the file part. It doesn't really, it just makes the model more complicated. It doesn't really change any of the insights of it. So I was like, okay, on the device, there may be some faces and there may be some names. And then the third type of thing is a cluster, which is a group of faces or names that crosses over multiple devices. And so that's what I started out with as our model. And then I set up some invalid states. I told Alloy a face and a name must be connected to a device, that you can't just have a face and name floating out in the ether, like without being able to trace it back to the device. The device is essentially the parent of the face or name. And that clusters must have something in them. They can't be empty, right? You don't have a cluster if there's nothing in it. But that the third rule that I gave it is that the cluster and devices are not dependent at all, because clusters kind of collect data from multiple devices. There isn't really a hierarchical relationship between clusters and devices. And then one of the great things about Alloy, and why it's where people tend to start when they start playing around with this world, is that you can run the model checker, but it has this great visualizer. And so you run the model and it'll give you some output in a sort of traditional fashion. And then you can say, hey, visualize that output for me. And it will generate a visualization of a valid model. And that gives you something you can sort of put in front of people and kind of stimulate conversation with them. So it generates this. And it's like, is this, giving you the specifications you've given me, is a valid model of this scenario? We have a device, there's a face on the device, the face is in a cluster. That looks great. But as soon as I put this in front of the engineers working on the system, the first question became, is it a cluster if there's only one face in it? Like, we know it's not a cluster if there's zero data in it. That doesn't make any sense. But can we have a cluster of one? And lo and behold, people disagreed about the answer to this question. The requirement was not clear. We had one part of engineering building with this like cluster of one mentality, and another part of engineering assuming that that would never happen. And by basically modeling it out and putting it in front of people, we got the ability to have that conversation and actually get a consensus around what we were building. We would have different scenarios like this. Like, okay, we have a device, and on this device is a document with a name in it, and also on this device is a photo with a face in it, and they're both in a cluster, but they both appear to be in the same cluster. Is it possible for names and faces to be in the same cluster? And like, if it is, how on earth does the system do that? Because that's a whole level of functionality that if you didn't know, you needed to sort of associate names with faces in a system like this. That's like a fairly large amount of work that you weren't aware you needed to do in order to deliver. So this is a really great thing to put in front of people and go, is this a valid state? Or does this a cluster just purely faces and purely names and like no mixing in between? And so this is often where people start with modeling. They don't go into like the verification, like writing assertion stage of things. They start with just using these tools to generate as many valid examples as possible and iterating through the valid examples and trying to figure out where the edge cases are, where things are technically valid, but yet undesirable or incorrect given our understanding of the system. And it's really valuable to even to do something as simple as this, because people very frequently disagree about what a valid state is in real on an operating system. So to be able to kind of prioritize having those conversations with different parts of engineering teams that have to work together helps them work together much more effectively. When we get a little bit more complicated with modeling, then we have the ability to get a little bit more advanced in how we use something like Alloy, and we can start to write assertions. We can start to come into that experience and say, like, Alloy, I know you can generate as many valid examples of this model as possible, but I want you to focus on proving or disproving the following statement, that given these controls, you will never find a valid implementation of this model where this is true or this is false. And that's where you start to get the really powerful uses of this type of modeling, is actually going in specifically and saying, I want to prove that this function does or does not do the following thing. Okay, use case 2, system integration. Again, very common scenario for a lot of people. We have processes that are usually broken up over multiple services and their transactions between services, right? So how important are the order of events? And do our controls actually prevent the failure that we think they're supposed to? And so we go to the TLA plus, right? So TLA plus is a similar idea to Alloy. It's a little bit different because it emphasizes time, whereas Alloy emphasizes relationships. And so we break out our model into a series of steps. And what TLA Plus does is it runs those steps in all sorts of different orders. And you've given it a set of rules of like what should be true. You've either always true or eventually true. And it will look for violations of those rules given the information that you've given it. So this is particularly great for things like race conditions, any kind of concurrency issue, anything like that. This is the TLA Plus is a really great tool to model those kind of scenarios. So how do we build those kind of models? Well, the first thing I tell people is that when we're dealing with modeling, we're generally dealing with state machines. So think about the problem and the technology that you're working with, and like, how can you make this look like a state machine? That may mean that you take all of the steps in the process and think about the transitions between one state to another, and that becomes your steps in your model. It may look like something else. There are definitely forms of technology that look like state machines out of the box, and so they're very easy to start to reason about in this fashion. But just thinking about like, what are the potential states the system can reach, and like, how does it reach it? What brings it to that state? And then writing that process of going from step to step as the code in the model. And then when we're defining constraints, the things that we're checking against, then we're really asking ourselves like, well, okay, of these states that I've brainstormed out as possible states and the transitions between them, what states should be impossible? And like, how do we know when we've gotten to an impossible state? What would be true if we've reached the impossible, or what would be false if we reached the possible? And so what's great about TLA Plus is that it has a domain-specific language called PlusCal that fits on top of it and compiles down to TLA Plus that looks very similar to conventional programming languages. So a lot of times people gravitate towards TLA Plus because, unlike a lot of other modeling languages, its syntax looks more like programming and less like mathematical proofs. So this is an example from a great book written by a good friend of mine, Hilo Wayne, called Practical TLA Plus. It's probably the best resource to getting started with this type of modeling. He goes through a lot of really easy, accessible answers and like builds out the code with you little bit by little bit while explaining the concepts behind TLA Plus. This particular example is a little chunk of code that's checking our error checking when we're trying to withdraw money from an account, because obviously that's a situation in which, because of the way we do bank transactions, it's entirely possible that we approve a withdrawal when there's actually not enough money in the account, simply because of the timing of transactions. And so this is a little chunk of code that represents what we think is an appropriate control for preventing that from happening. And using this model, we can sort of check all of the various ways that different transactions can hit that account and sort of prove that this little control that we've written in does in fact prevent you from being overdrawn. So this is one possible application. Use case 3, refactoring, which I'm sure like a group of menders, like this is like a big deal, right? Like, how do we, throughout time, we've accumulated a certain amount of technical debt because we've added requirements, we've changed requirements, and we're always faced with these questions of like, we have this existing code, is it still actually written the way that's most effective? Do we still need it? Have we introduced subtle bugs by changing behavior just slightly here or there? Like, how do we use modeling to help us be better refactors? And so we go back to Z3 as a concept here, right? Like, what you'll learn as you get more and more into modeling is that a lot of the tools that we're using are actually built on top of Z3 or something similar. They're built to give Z3 more expressiveness, because the files that we produce when we're dealing with SAT solvers and SMT solvers are very long files, even for very, very simple concepts, because the amount of states they have to represent is impressive. So that leads to many, many lines of code, and it's somewhat overwhelming to write SMT just from scratch, right? So there are all sorts of tools that are put on top of S3 to sort of increase the expressiveness and help people write better models. But everything that we do with computers, we can somehow, some way represent as a logic puzzle, because computers themselves compile all of our code down to binary, which in and of itself is a true-false question, right? It's like you're either state 1 on or you're state 0 off. So every piece of code that you write that compiles down to binary and is run through logic gates through a CPU can be at some stage represented as a logic puzzle. The tricky part is not representing your code in the structure of logic. The tricky part is figuring out what is the puzzle actually solving for, right? We have to figure out how we're writing those constraints, like what states are good and what states are bad, so that we have given Z3 something to solve for. So there are a couple different things that we can do. The first thing that we can do is we can represent our code in these kind of logic puzzles and just check to see that it does what we think it does, right? Stuff we've already talked about. We can also test for its security. Does it allow any states that were not desirable to us to occur that we were unaware of? But the second thing that we can do when we start to represent our code in these kind of logic puzzles is we can actually, what we're writing are small components, and then we can give Z3 a set of inputs and a set of outputs, and we can say, hey, Z3, if for all of these inputs, take some combination of the components that I've encoded in SMT and produce a program where the input creates the output. And when we start to do that, we start to get into what's called code synthesis, right? So what code synthesis does is it writes alternative programs that take our inputs and produce the same outputs. And the benefits to doing this is that you may end up with a different point of view on a set of existing code than you started out with. You can say to Z3, I want you to produce a piece of code given these set of components that does the exact same thing as this piece of code, but does it with fewer lines of code, or does it faster, or does it in using less memory, or does it, you can sort of start to write little optimizers to evaluate existing pieces of code once you start being able to think about code in terms of components and then inputs and outputs. And so like, this is really like the cutting edge of like what people are doing and exploring with these kind of modeling systems is, can we actually use it as a feedback loop for real life programmers to get them to program more efficiently or program more in line with each other, things like that. And so what's next? Like, this is all great. Like, this is really just an exciting kind of world to interact in, but it actually doesn't cover all of the things that can go wrong with computer systems. Like, what is left to cover where there isn't really great tooling. And this is the world of what's called system dynamics. And so this is the stuff that I'm really interested in. I'm doing a lot of like a little bit of research and a little bit of development around what the tooling could look like for this state. Because when we're talking about system dynamics, we're talking about feedback loops. And a lot of practical tech problems that at least I deal with on a regular basis with systems, they're really about feedback loops. They're not really about algorithm correctness right? So one example is a auto-killing an unhealthy server, right? I want a load balancer to be able to kill an unhealthy server. That's not something I want to prevent from happening. But at the same time, I definitely have seen outages and experienced outages where there's some configuration setting that's been changed that means that the load balancer is doing nothing but spinning up servers and killing them, spinning up servers and killing them. And the system is unresponsive because we've gotten into this feedback cycle that's unhealthy. Right? Same thing with like rollbacks or freeing memory. We don't want to be able to prevent systems from doing these things. We don't want to say that these things are states that shouldn't be happening, but the context of how they're happening and when they're happening is significant. So we're looking at problems. How do we solve problems using the same kind of modeling where the action itself is not problematic? It's the context of that interaction. And really what we're dealing with is the difference between an impossible and an undesirable state. And this was the thing that took me a really long time to get with formal verification. But once I got it, I was like, all this tooling makes sense, right? Is that these tools that I've been talking about are really looking at impossible states. And when we're talking about feedback loops, we're looking at undesirable states. And so most software engineers are not going to sit down and write algorithms, brand new algorithms. They're going to work from existing packages and modules. They're going to work from existing open source solutions. And a lot of what they're doing day to day is going to be either CRUD type work, or it's going to be kind of daisy chaining different solutions into a workflow where tech A connects to tech B, tech connects to tech C. And we can use modeling to like look at these processes and find bugs in them. But what we're doing when we're looking at those kind of things is a small number of impossible states and a large number of potentially undesirable ones. So we really have to start to think about how do we use logic to think about undesirable states and not just impossible ones. And so the person who did the most work in the state, the sort of father of system dynamics, is a man by the name of J. White Forrester. And he's one of those early CS legends, working in the time of Alan Turing and all of the real greats, and has the medals to back it up. He basically was the inventor or one of the inventors of magnetic core memory. He didn't do it by himself. Developed the forerunner of RAM, so like a really critical person in the early days of computers. But as he was working at MIT, he got to a point in his career around the 50s, mid 50s, where he thought, like, we've solved all the hard problems in computer science, so I'm going to move over to these more policy and economic based systems. And that's when he started working on these things he called system dynamics. And the reason he got into it is because GE reached out to him and sort of said, like, we're having problems with our inventory. Like, we either have too much inventory or too little inventory. And they reached out to him because they thought, build us a computer, the computer program will fix this problem, and then we will always have exactly the right amount of inventory. And when he looked at the problem, he realized that it had the same shape as a problem he had seen when he was involved in the war effort, where the first time people fired a gun, in this case a cannon, they missed the shot. And then the second time they fired it, they tended to overcorrect. And what would happen is that people would wobble in between these wrong states, back and forth, isolating until they finally got their targeted right. And this led to an entire branch of science called control theory, where we were looking at the environmental factors and changes that needed to be factored in to the amount of force that you were exerting to accomplish a particular task. So there were some counteracting forces and there were some intensifying forces. And if you were not thinking about those forces as you were doing things like targeting systems, then you would see these wild oscillations as you were trying to figure out exactly the right way to do it. And so the thing that he worked on the most when he was involved in this was actually the steering of ships and factoring the forces of waves or the direction of wind to figure out how exactly you should steer a ship. But he thought, like, you can do this with these kind of more nuanced systems as well. Like, it's really clear how to do this with mechanical systems and not super clear how to do this when we're talking about economics, or in the case of the technology we're talking about, like load on a web server, right? So it gets really clear how we measure the direction and speed of the wind when we're trying to steer a ship. It's not really clear how much force is involved when the price is rising on inventory, right? It's not really clear how much load is in a single page view. We might have a range of possible values, but it's not really clear. There's not really a one right answer to that. So applying the same principles of control theory into these more nuanced systems is how you develop system dynamics. And so I've been thinking a lot about system dynamics for technical systems, and this is what I think is like the future of this type of modeling, is figuring out how do we think about things like CPU and memory and data and requests as what Forrester would call stocks and flows, being like stocks of things like resources that have piled up and accumulated, and flows which are changing the amount of stock in a given part of the model. And the reason why I gravitate towards this style of modeling, and I'm so excited about it and think it's like the future of modeling, like the next frontier for a lot of this formal methods, is that when you start thinking about things in terms of stocks and flows, it has actually a much more expressive language for modeling complexity and coupling. And the work that I did in legacy systems, a lot of what was going on in a system was about the level of complexity in various parts of the system and the tightness of the coupling of different moving parts. And changing that ratio could vastly improve or diminish a system's overall stability. And so for example, we might want to model something that looks more like this, where we have like a pool of VMs, and we know that we want to keep their CPU at a certain level in order to consider them healthy. And we have a certain number of requests coming in and a certain number of requests being served out. And we can sort of think about this in the language of stocks and flows and sort of put some rough numbers behind them and ultimately build a model that allows us to kind of run these simulations for different loads at different times, right? And we might create a model that gives us like sort of like goes up to 8 steps and have to answer this question of like, well, all right, now that we're getting to the limit of what we think these VMs can handle in being healthy, like what is the next state? Is the capacity continuing? We're going down, but we're going down by how much? Are we going down by a little, or are we going down by a lot? And the answer to that question really depends on whether or not the two things that are going on, the measuring how much load the current pool of VMs is under and scaling it up or down, given that, are coupled or decoupled. If you couple these two things together, you get a different set of numbers as you run that simulation. And if you decouple them, you get another set of numbers as you run that simulation. And so just as when we're looking at TLA Plus, we are playing with different ways of representing controls and steps and the breakdown of steps, we can also build models that look at different ways of coupling and decoupling certain processes and seeing how that changes the overall system's behavior. So this is kind of a project I'm currently working on because I think that this is a hole in what is currently available in modeling solutions that's really useful for day-to-day software engineers, and particularly useful if you're like me and you deal with like large, complicated, possibly old systems. And so this is sort of my pandemic side project. I have spent a lot of time playing around with the prototype language to do this. I did a whole podcast about it, which has 2 seasons and is on hiatus while I figure out like various things around writing a compiler, but will return for its 3rd season at some point, where I kind of share the things that I'm learning as I'm going through this process and like why I think this type of modeling is especially valuable in the future. But let's like just sum it up. So with the current state we have with formal methods is still really useful in like helping us think about how we do modernization, because it allows us to simulate requirements and explore edge cases. It allows us to hunt for really tricky bugs, particularly around like concurrency and distributed systems. And it could potentially, when we get really comfortable with it and go to the more advanced cases, could help us optimize the existing code by generating alternative code using these programming puzzles. But there's also a really healthy future for this type of modeling as we start to go more and more into the expressiveness that programmers need on a day-to-day basis and the challenges that they face on a regular basis beyond algorithmic correctness and start thinking about feedback loops and that exciting landscape. So that concludes the formal part of my talk, and I'd love to spend the rest of the time that I have with you guys answering any questions you might have. Toggle back so I can see the chat window. I'm happy to chat.
Awesome, thanks, Marianne. I don't see any questions yet. Yeah, that was one. There's also a slight delay on the broadcast, so I think you and I are synced up pretty well right now, but there's a few seconds of delay.
Just be like, greetings from the future.
Yeah. Yes. Yes, that was fantastic. So the when you started talking about like optimization, is there any value in like some of the optimizations you mentioned? I'm doing that, like you could be done like in an algorithm. Is there any value in like trying to like build a system to like do that for you automatically, or is that hard because it has to know like what you're trying to optimize for? So like, are you trying to optimize for speed or number of instructions? Or
yeah. Yeah. So I'm not a huge fan of not unstructured, but like a kind of free range models. I think models are most effective when you essentially have a hypothesis and you're using it to hypothesis test and like be very structured in your exploration. A lot of stuff that's around code synthesis is very academic. It's very research-based. It hasn't quite seeped into the tooling, but it's really exciting because it will eventually get there, right? It will eventually start to be incorporated into IDEs and other tooling that people can use. And I think one of the things that I find the most interesting about code synthesis isn't necessarily the optimization of code as it is the standardization of code that is being written by multiple parties, right? Because we've all had that scenario of people having broadly different styles and working on the same code base. And if you can sort of use code synthesis to partner with things like linting in order to sort of nudge people in the direction of taking a certain style and honoring certain conventions, but in a more flexible way, because I think we have tooling to enforce conventions, and I think we've all been annoyed by it at some point, where it's told you, don't do it that way, do it this other way, and you're like, there is no reason for you to deny me the freedom to do it this way, right? So being able to use code synthesis to start to nudge people in the right direction so that people are building things in roughly the same way and understanding it in roughly the same way. I'm really excited about like what's going to develop over the next 5-10 years around that.
Yeah. All right, so some questions have started to filter in. If you'll be able to see them if you stop.
Yeah, I love this question. Are stocks and flows more probabilistic? And do you do proofs on that as well? Because this was like a core part of the research challenge that I was facing earlier this year. So like I am like, this person is not a plant, but I feel like they are. You literally just pulled it out of my brain. This is perfect. So yeah, that's the big challenge I've had with stock flow models that I was looking to solve, is that generally speaking, when we talk about like say, for example, the state that a VM might be in terms of its memory managed, right? We don't know exactly what state that is, but we have a range of states that we know are okay. We have a range of states that we know are not okay. And so when I first started building models, like the system dynamic models, I was actually using TLA+. And it was an interesting experiment and a super frustrating experiment, because I would build the model and then TLA Plus would give me a result that said like, well, if all of your VMs are at 100% capacity, then the system crashes. And I'm like, well, no shit, Sherlock. Like, I did not need a model to tell me that, right? And so through those early experiments with TLA Plus, what I realized is that probability plays a huge role in these kind of models, because there are states that are possible but are not likely, and therefore I don't really care about those states. And so what I've been working on with Fault is how do we represent that in the language? And I've been using the concept of uncertain types, where instead of defining a value for something in a model, you can define essentially a normal distribution. You can say, this is the average that this value usually is, and this is the standard deviation. And from that, we can deduce whether a given state is likely or unlikely in that model. And so we went through this whole thing of like, how do we implement that in code? Because if you know anything about probabilistic programming, a lot of the methodologies are based on the assumption that variables are independent and that they're not in they're acyclical in nature, that they're not in a self-reinforcing feedback loop. And obviously in a system dynamic model, everything is a dependent variable and it's all cyclical. So there was some question of how best to do that. And the conclusion that I came to is that I wanted to go back to the SMT stuff that I felt very comfortable with, which is a scary thing for me to say out loud. I never thought I would say I feel comfortable with SMT, but there you are. I wanted to go back to that. I wanted to run the model and have it solve for the uncertain types that were in the model, and then take the output of that and compare it to the distribution and assess its probability that that would actually be a state that would happen for real. And I thought, if we can do that, that might actually be useful. We might actually be able to say, like, this circumstance will lead to your model's failure given the constraints that you have put in place, the assertions that you have made in the model. But this state is also likely or unlikely.
That's awesome. So we're at time, and at the same, we also don't have anything else going on the stage. We do for the next 5-10 minutes. We do have the retrospective session starting at 4 p.m. That'll be over in the sessions area. So there's still a few questions left, Marianne, if you just want to hang out here and,
sure,
and answer those. I'm going to go ahead and leave, which I don't think is going to break anything. So I'm going to have to turn off my video, and I'll just like step away from the computer.
Okay.
but keep broadcasting so you can continue to interact with people here.
I don't know that I know how to stop broadcasting, so
Okay,
I just know how to leave.
I'll figure that out. Thanks.
Okay. So another question that's in the chat is, I have any guidance on how to determine whether something should be an invalid state or an undesirable state? Yeah, I think invalid states are conditions that are impossible. That's the easiest way to describe it. Also, I would say conditions that are dangerous. So I was talking about having a load balancer auto kill a server. Like, that's an undesirable state because we have many situations in which that state is not dangerous and is perfectly fine. However, something like a buffer overflow, right? Like that, it's very hard for me to think of a situation in which that is an okay state, right? Like something like that is definitely a thing where we want that to be an impossible state, right? So just thinking about it in terms of like, how dangerous is the state? And do we believe this state to be impossible is a really great way of like sorting out the difference between, is it invalid or is it just simply undesirable? I also really like this question about speech-based database modeling. There's been some great work around different ways of using both the techniques I talked about here and also making use of things like control flow graphs around debugging and like what is the interface that a programmer looks at when they're trying to make sense of systems. There's a project that I've sort of been poking more and more and more around. It's called the Glamorous Toolkit. And it's roughly connected to a project called Moose. And all of this is about treating code as if it is data and reasoning about it as if it is data. And so it's all written in Smalltalk, which is slightly irritating, actually. but you know, as a person who loves legacy systems, I feel like it was only a matter of time before I had to learn Smalltalk. And so I am optimistic that projects like this may create new interfaces for people to interact with code and reason about what code bases are doing and improve the onboarding experience to code bases, where we're figuring out what a given chunk of code does much, much faster, and therefore onboarding engineers onto it much, much faster. Oh, I just realized there is a little Q&A tab. Are there still ways to gain value from modeling if current existing systems? Yeah, definitely. I mean, I would say that if you don't understand the system and it's complicated, the best way to try to understand it is to try to model it. And a lot of times what we'll do is we'll have somebody who feels really comfortable with a particular modeling language kind of pair up with engineers that feel really comfortable with the existing system and sort of like write a specification for them, and then come back and say, like, is this specification right? And get them to confirm or deny, and then run the model and say, like, is this output, like, is what the model is telling you is a valid state? Is this in fact a valid state? And that sort of helps you sort of figure out what you don't know and like get those small little bits of institutional knowledge that are buried in the mind of so many software engineers out in the open. Could the system dynamics approach with something like fault-laying ultimately be helpful to help people face and contend with nonlinear effects? I don't know, actually, because maybe, but system dynamic models tend to be linear in nature. And we start getting into an area where I get very nervous because I don't feel super 100% on the math when we start moving to nonlinear processes. I would probably think that it would be hard to get a reliably good outcome with that, but I don't know. I get when I get far enough to like put in like serious beta testers, I will let you know, and you can come and tell me how bad it is. Let's see if there's anything on the QA tab that we haven't already. I don't know if the GE still has the inventory problem, but I do know that an entire discipline of work came out of it, so I would declare success anyway. The best way to become familiar enough with these tools is to use them. And it is admittedly a steep learning curve, but there is actually developing more and more a really great supportive community around it. I would say that Alloy's community is a little bit more open and welcoming than TLA Plus's community. But still, like it is a thing that has become a hot topic in academia, which means there's a whole bunch of young computer science masters and PhD candidates that are writing papers and talking about Twitter and talking about this over Twitter and stuff like that. So the best way to get good at it is to simply jump in, start using it, and just keep using it and asking for feedback and finding problems. I'm spending a lot of time now kind of trying to figure out performance issues with Z3 because it's SMT. One of the downsides of it is that it's NP complete, which means there's no guarantee that it'll ever return any result at all. And so there's like an oral tradition of ways of writing specs that help you avoid like having a really, really, really long runtime of your model or having it never return, versus phrasing the question slightly differently and having it return in a more reasonable fashion, right? And like all of this is like oral tradition. No one has written it down. There does not appear to be a manual or any kind of advice or documentation about it. So I've been sort of digging into building little models and like doing benchmarking and then asking people why is this running better than this other thing, and trying to figure out like the exact structure of how it's working under the hood. Oh, somebody wants me to post a link to my book. Yeah, sure. I could definitely do that. Actually, I'm ashamed that I don't have one ready. Let's see. Any advice for getting a group past this sort of learned helplessness feeling on legacy projects? I mean, yeah, the struggle is real, right? And one of the things I talk about a lot in the book is this idea of building momentum and like what sort of things build momentum and what sort of things kill momentum and like how to build and protect your momentum. And it's everything from how do you design technical conversations so that people feel productive in them to how do you articulate value. And so the best piece of advice I have for getting people past that kind of helplessness is to essentially think of all the things that you could potentially change about that system in terms of value add and try to estimate or quantify their value add as much as possible. It doesn't have to be perfect and it doesn't have to be accurate, but just giving yourself an idea of like, I think I'm going to get this much value out of doing this versus this much value out of doing it. Helps guide the conversation and decision making quite a lot. Often I'll use a structure like SLOs to sort of help figure out like how to quantify value add, and then prioritizing the things that you think are going to provide the most bang for the buck as early as possible. Because one of the things that I've found on systems where people feel kind of helpless is that as soon as they see other engineers starting to make progress on things and like see the numbers on what we're monitoring getting better, suddenly everybody is inspired. Everybody has new ideas of how to make it better. Everybody is motivated in the right direction. So the sooner you can get to like real strong value add early in the project, the better you're going to have, time you're going to have getting over that learned helplessness bump. Which one of these lessons do I think is the one that's overlooked more often? In terms of modeling or in terms of something else? I'm going to answer this question in terms of modeling, I think. I think for me, the thing that a lot of people miss with modeling is that they overestimate the value of directly linking the model, the spec to actual code, right? So a lot of the things, the tooling that people request when they first start modeling is something that will cross-compile to actual code. They want to write their models in Alloy or TLA Plus or Z3, and they want to cross-compile to another language from that model. So you run the model, you prove the model is correct, and then you click a button and it writes your code for you. I think that we overestimate the value of that. I don't think that is as valuable as people assumed it would be. I think a lot of the value of the model is the critical thinking component, the communication component, the reasoning about systems component, and that if we try to link it really strongly to implementation details, then we're going to lose some of that value and maybe not generate code that is actually readable to other software engineers. In general, I'm not super bullish on auto-generated code in any format, even when we're talking about code synthesis, because it affects what is good to an algorithm is not necessarily what is readable to a human being. And at the end of the day, human beings always have to read it. So I think people sort of overestimate the value of being able to verify something and then tie it directly back to a given implementation. All right, well, we're at 4, and I want people to be able to experience all aspects of this event. So thank you so much for listening. It was a real pleasure to come and talk to you guys about my favorite things. And again, you can find me on Twitter or Medium under the handle Belmar, and I'd love to continue the conversation kind of offline and in sync with async with you guys. So